This lecture will be going through how to actually solve equilibrium problems. And it's a very short lecture, at least like the number of slides. And the time of the actual recorded lecture might be a little bit shorter than the others, but if you're actually working through these problems, I'm guessing it'll take, for probably longer or as long as some of the other lectures do. So just kind of be aware of that if you're judging time. If you're really doing this correctly, you'll probably be stopping it and trying to work through these problems, or at least paying attention to how they're worked and maybe, watching the problems, solving the problems a couple times. So just be aware it's probably going to be a little bit longer than the clock time. Right, and on the title slide, this is an illustration of what we'll be going through with these, and that's the ICE tables that I'm sure a lot of you have seen before in high school. And what that stands for is you have an initial value of concentration, then you have a change in that concentration, which you usually abbreviate as the variable x, and then you have an equilibrium concentration, which would be the initial minus whatever the change is, and then you solve it from there. Okay, last time we started our talk about equilibrium, we introduced equilibrium, and we introduced the equilibrium constant K and the reaction quotient Q, and then we used Q and K to determine which direction the reaction would go. Okay. What we're going to go through today is the steps to solve equilibrium problems, and that is specifically how to utilize reaction tables, or also known as ICE tables. And this is from section 5 of chapter 17. Okay, so solving equilibrium problems. Okay, if equilibrium quantities are given, which is the easiest example, you simply substitute those into the expression you have for the equilibrium constant or for the reaction quotient, and calculate its value. Okay? But oftentimes those concentrations at equilibrium aren't known, or they're not given to us in the problem. Okay? If only some of these equilibrium concentrations are given, then you have to use a reaction table to calculate them, or the rest of them, to find the full expression and calculate a reaction, a equilibrium constant. Right, and what the reaction table shows is that at first you need the balanced chemical equation, as with most chemical problems that you're going to solve. Then you need the initial quantities of the reactants and the products. That's the I. Then you need the changes in these quantities, and that's usually something you don't know, so you use the variables, most commonly x. And then finally, the equilibrium quantities. So if we use this example, a study of carbon oxidation in an evacuated vessel containing a small amount of powdered graphite is heated to 1080 Kelvin. Gaseous CO2 is added to a pressure of 0.458 atmospheres, and carbon monoxide forms. At equilibrium, the total pressure is 0.757 atmospheres. Calculate the equilibrium constant, K sub P, in terms of pressure. Okay, so we have our balanced chemical equation. Right, then we write our reaction table, or ICE table. So the initial amount that we start with, for CO2, it's listed here as 0.458 atmospheres. Carbon graphite is a solid, so if you remember back, we really don't need to consider it because technically its concentration doesn't change. Okay? And it's not going to factor into that calculation for equilibrium constant. And then we, at least initially, we're not starting with any carbon monoxide. So initial value for that would be 0. Okay, how do they change? Well, we know the reactant CO2, that's going to go down, and we know carbon monoxide will go up, and it will go up actually 2 times as fast as carbon dioxide goes down, because the mole ratio here, we have 1 mole of CO2 and 2 moles of CO. So if we use the variables x, right, we're going to be losing carbon dioxide, so we can write in minus x for the change of that. And carbon monoxide we're going to be gaining, so it's going to be a positive value, and it's going to be 2 times the amount that we lose of carbon dioxide, so we can write in plus 2x for that change. Then the equilibrium amounts, we just add the initial and the change together, and that's how we get the amount at equilibrium. Okay, so once you have those equilibrium amounts expressed in terms of your variable x, you use other information given in the problem to solve x. So in the problem, it stated that the total pressure at equilibrium was 0.757. Okay, that's the total pressure. So you know that that has to be the 2 pressures of the 2 gases have to equal that total pressure. Okay, and you also know if we put in, back it up to the table, right, if we put in our 2 equilibrium values for those concentrations, those have to add up and equal that total pressure. Okay, so there we get this final expression from the reaction table. Okay, and then you can rearrange this and do algebra to solve it. And x is 0.299 atmospheres. So at equilibrium, and then you can go back and plug this value for x in, right, in both of these expressions. So at equilibrium, the carbon dioxide concentration would be 0.159 atmospheres, and carbon monoxide would be 0.598. And we can then write our expression for equilibrium constant. Remember, it's the products over the reactants. We do that, and we get the equilibrium constant of 2.25. Okay, so that was a basic problem. We're going to work through 5 more of these. The first few are very similar to that. They do get more complex. So the first problem we'll work through, in order to study hydrogen halide decomposition, a researcher fills an evacuated 2-liter flask with 0.2 moles of HI gas and allows the reaction to proceed at 453 Celsius. Okay, so the reaction is 2HI decomposes into H2 plus I2 gases. Okay. At equilibrium, the HI concentration, so our starting concentration, is 0.078 molar. Calculate K sub C. Okay, so the information they give us here, they give us a volume and an amount of HI gas that we're starting with, an initial amount. With those, we can calculate a concentration. These tables are, in general, they're in terms of either concentration or pressure. So just a straight number, moles of compound, we don't really use that in these tables. We tend to use concentration or pressures. So they're not giving us that concentration, but they're giving us enough information to calculate that initial concentration. And then they're also giving us that final concentration at equilibrium. Okay, so let's try to set this up. Oop. Okay, so remind ourselves our reaction. We have 2HI decomposing in equilibrium with H2 and I2. Okay, and then we can calculate our initial HI concentration. I'll just designate that as that subscript naught. That means initial. So we have 0.2 moles in a volume of 2 liters. So that's a concentration of 0.1 molar, or 0.1 moles per liter. Okay. So now let's do our table, our reaction table. So our initial concentrations here, we just calculated that for HI is 0.1 molar. And presumably we don't have any of the products at the start. Sometimes the question will tell you you have a certain amount of the products to start with, but since they didn't say anything in this case, you can assume we have 0. Okay, the change. Okay, how does this change? Well, we're going to lose some concentration of the reactants, and we're going to gain some of the products. So we can say, in this case, we're going to be a negative value for HI, and we can just call this 2x. Sorry, that 2 looks like a 3. Okay, and that's because there's this coefficient of 2 out in front of it. You could just call that x, but then you'd have to, on the other side when we're doing the products, you'd have to call those 1/2 x just because of the stoichiometry in that balanced chemical reaction. So it's probably easier not to deal with halves and just call this 2x. And these would be x's, right? Because they have, a 1 out in front of here for their coefficient. And their products, so they're going to be gaining amounts, concentration at equilibrium. Right, and so that at equilibrium, it's initial plus the change. So for HI, we're going to have 0.1 molar minus 2x. And for both of the products, we just have 0 plus x, so we can just write x for both of these. Right. Now we need to solve for our equilibrium concentration of HI. Right, equilibrium concentration of HI. We have that expression in our table, 0.1 molar minus 2x. And in the problem, they actually tell us what this is. It is 0.078 molar. So now we can rearrange this to solve for x. So 2x equals 0.1 minus 0.078, which is 0.022. Okay, then we divide by 2 to get x, and that is 0.011 molar. Okay, so our concentrations at equilibrium for HI, right, this was given 0.078 molar, and both of our products, we just calculated that, are going to be 0.011. Okay, now we can solve for our equilibrium constant, K sub C, and remember that's just going to be our product concentrations over reactant concentrations. So that's an awful H, but H2 times concentration of I2 divided by concentration of HI squared. Okay. And then we can just plug in our values for those concentrations that we calculated from our reaction table. So we're going to have 0.011 times 0.011 divided by 0.078 squared. And doing that, we get a value of equilibrium constant for this as 0.0199. Okay, so that's a pretty basic example. We're going to try another example. Right, in this problem, we have the conversion of methane to other fuels. Chemical engineer mixes gaseous methane and water in a 0.32 liter flask at 1200 Kelvin. At equilibrium, the flask contains 0.028 moles of CO and 0.084 moles of H2 and 0.045 moles of CH4. What is the concentration of water at equilibrium? Okay, and we're given for this the equilibrium constant of 0.26. Right, so in this question, the previous question we were trying to calculate a equilibrium constant. In this question, we're given the equilibrium constant. We're trying to determine a concentration of one of the reactants at equilibrium. Okay, so we're sort of working at this backwards compared to the first problem. Okay, so again, we're going to always write our chemical equation balanced if you're not given it. So we have methane plus H2O, both gases, so they factor in to our equilibrium expression. Go to carbon monoxide plus 3H2. Okay, so now we're going to write our ice tables. And we need to calculate our equilibrium concentrations. And this question's a little bit unique in that if you go back and read it, we're not given a initial concentration for any of these, okay? We're only given the amount at equilibrium for three of the components, and we're given a volume. So we're given the moles and a volume. We can calculate concentration, but those are actually at equilibrium. So in a sense, this is a little bit simpler. We don't have to worry about initial or change. Let's go through these. Methane was 0.045 moles in 0.32 liters, which was something like 0.140,625. Okay. H2O, we don't know that one. Carbon monoxide, we had 0.028 moles divided by 0.32 liters, which is 0.0875 molar. And finally, H2 was 0.084 moles in 0.32 liters, which is 0.2625 molar. Right. We're given also a value of equilibrium constant at 0.26. Right, so this concentration is going to be our variable x, H2O. We can write this expression for K sub C, right, as just the concentration of products over concentration of reactants. Now we plug our variables in, or excuse me, we can plug everything in except for our H2O concentration. So this is equal to 0.26. All right, we can plug in. Actually, let's rearrange this first and solve. Before we plug anything in, it's simpler just to rearrange to solve what we're looking for. So we're looking for H2O concentration. So if we rearrange that, right, you'd multiply both sides by H2O and you divide both sides by Kc. So you're just kind of switching the places there. So that's 3 CH4 and K sub C. Sorry, that is K sub C. Okay, now we can plug everything in because we know all of those. All right, so 875 times 0.2625 to the third power divided by 0.140625 times Kc, which was 0.26. Okay, then we simply just plug that in, solve. H2O concentration is 0.0433 molar. Okay. Right, so there's an example of a question where you know you probably don't really even need to write the reaction table because we're already given the equilibrium concentrations. Okay, the final sort of basic ice table equilibrium problem here. Fuel engineers use the extent of the change from carbon monoxide in H2O to CO2 and H2 to regulate the proportions of synthetic fuel mixtures. If 0.25 moles of carbon monoxide and 0.25 moles of H2O gases are placed in a 125 milliliter flask at 900 degrees Kelvin, what is the composition of the equilibrium mixture at this temperature? And you're given a value for the equilibrium constant. Okay, so this is probably more of a classical type of equilibrium solving problem. Okay. So our reaction is carbon monoxide and water in equilibrium with CO2 and H2. That's plus H2. Okay, now we can write our equilibrium reaction table. And we're given a value for carbon monoxide and H2O gases. And we're told we have 0.25 moles of them in 125 milliliters. Right, so 0.25 moles in 125 milliliters, which would be 0.125 liters. Right, you do that math, and that would equal 2 molar. Right, and H2O is the same, so we can just write in 2 molar is that concentration. Right, and we're not starting with any products, so we can put zeros there for the initial concentrations of both of those. Okay. Next, we have our change. Right, we're going to be losing reactant concentration and gaining product concentration. Right, so both CO and H2O are going to be minus X's, and CO2 and H2 will be plus X. So at equilibrium, these expressions would be 2 molar minus X for carbon monoxide and 2 molar minus X for H2O, and 0 plus X, which is just X for both CO2 and H2. All right, now we can look at our equilibrium constant. Okay, we know this is 1.56, right, given in the problem. So 1.56, and we can write this out in terms of our concentrations at equilibrium. It's going to be products, CO2 and H2, divided by reactants, CO plus H2O. So for those concentrations, now we can just plug in our expressions from the reaction table. So both products will be X, and both reactants will be 2 minus X. Right, so if we, distribute those through, that's X squared on top and 2 minus X. Whoops. 2 minus X squared on bottom. Okay. If we try to solve this now, right, doing the square root of both sides, square root of 1.56 equals the square root of X squared divided by 2 minus X squared. So that, once you do that, just draw an arrow over here. Once you do the square root of both sides, you get 1.2489 equals X over 2 minus X. And technically it's plus or minus because you could have a negative value there for X, and it would, because it's squared, you would multiply a negative by a negative and get a positive. All right. Taking this a little bit further, distributing through 1.2489 multiplied by 2 minus X equals X. Then we distribute that 1.2489 through, so we'd get 2.498 minus 1.2489x equals X. And then if we add 1.2489x to both sides, we would get 2.498 equals 2.2489x. And then X would be 1.11 molar. Right, so then if we're trying to find the actual concentrations at equilibrium, we'd plug that value back into X, into these expressions. So 2 minus X would be 0.89 molar for both the CO and H2O concentrations. And the products would just be X, which is 1.11 molar. Okay. So just going back, I did mention that, right, you could have this plus or minus here for the square root. If you did a negative value there, you would come through and X would be a negative value. And so if you do end up with a negative value for a concentration, you know that that's not physically possible. You can't have a negative concentration, so you would just flip the sign. Okay. So there are other times when these types of problems become much more difficult to solve, and to solve them, it turns out it gets much easier when you use simplifying assumptions. Okay. If a reaction has a relatively small K, let me switch back here to laser pointer. Okay, if your reaction has a relatively small equilibrium constant and a relatively large initial reaction concentration, the concentration change X can often be neglected. So if you have, a really large amount of reactants and your equilibrium constant is, sort of small, so it doesn't really favor the products all that much, then you can sort of ignore your change in concentration, at least in terms of the reactants. Okay. If the assumption results in a change that's less than 5% of the initial concentration, we kind of consider this as not significant, and then this assumption is justified. And it gives you kind of these ways to calculate that, I guess you could say, down here. So we're going to kind of go through a problem using this assumption. Okay. All right. So we have phosgene shown here, potent chemical warfare agent that's now outlawed. It decomposes by the following reaction, right? Phosgene decomposes into carbon monoxide, which is poisonous, and chlorine gas, which is also poisonous, right? So it's a pretty awful gas. The equilibrium constant's given here, and you can see that it's actually like a fairly low equilibrium constant. Okay, this is at 360 degrees Celsius, by the way. Right, so we're supposed to calculate our carbon monoxide, chlorine, and phosgene concentrations when the following amounts of phosgene decompose and reach equilibrium in a 10-liter flask. So the first condition we have 5 moles. The second condition we have 0.1 moles. Okay, so in the first, just setting this up, right, we're talking about using simplifying assumptions. And we say you can use those when you have a relatively large reactant concentration and a relatively small Kc value. Okay, so in this case, in case A, we have a larger concentration there. So in this case, we can probably use this simplifying assumption. And in the second case is when we have a smaller reactant concentration. So this is where we're not going to be able to use that. Okay, so let's look at the first case. We have 5 moles of phosgene. Okay, so our reaction is phosgene goes to carbon monoxide plus chlorine gas. Okay. And we know we have 5 moles, and it's in a 10-liter flask. So initially, we're going to have 5 moles divided by 10 liters, which would just be 0.5 molar. And we don't have any products to start. Okay, our change now would be minus x and plus x for both. That's how we would normally write those. And at equilibrium, Right, normally we would say this would be 0.5 molar minus X. But using that simplifying assumption, we can sort of just ignore that change in terms of the reactants, because we're assuming that we're starting out with such a large amount relative to the equilibrium constant. Right, so we'll just ignore that and call this 0.5 molar at equilibrium. And the products would just both be X's. Okay. So now we write our equilibrium constant expression. And that equals our products over reactant. And we plug in our values from our reaction table here. So those are X's, and our phosgene concentration is 0.5, so that's what we started with. We're assuming that we don't lose that much of it, so this is going to be a good estimate. And we know we're given the equilibrium constant at 8.3 times 10 to the minus 4. So now we can solve for X, so X squared equals 8.3 times 10 to the negative 4 multiplied by 0.5. So that's going to equal 0.000415. And we take the square root of both sides. This is approximately 0.02 molar. Okay, was this simplifying assumption justified? And so that's when they give you, comparing the initial concentration you have of your reactant divided by your equilibrium constant. So that would be 0.5 divided by our equilibrium constant, which is 8.3 times 10 to the minus 4. Okay, when we do that, we get 602.4. And remember, that is greater than 500. I think on the slide back here it says it has to be greater than 400, but I feel like the book said 500. So either way, it's greater than that. So you can assume that this simplifying assumption is justified. We're going to be less than 5% error. And, on an exam, I'll make it very obvious to you if you can use this simplified assumption. I'm not going to give you an initial concentration and a equilibrium constant that equals 500 or 400 and try to make you decide whether that's going to be justified or not. And most likely I will kind of tell you to use simplifying assumptions on a problem if you are supposed to. Okay. The second part to this, this is a case where we're not going to be able to use those simplifying assumptions. So our reaction, again, right, in this situation, we had 0.1 mole divided by 10 liters, which would be 0.01 molar. Okay, that's our starting concentration of our reactant. And we don't have any of these products to start. And how do we know, right, that we can't use simplifying assumptions? again, you compare your initial concentration divided by your equilibrium constant. So 0.01 molar divided by 8.3 times 10 to the minus 4. That it equals 12, which is less than that magical 400 to 500 range. So we can't use this. Okay. So we have to do it the long way. Okay, so change, again, we're going to lose reactants, gain products. So plus X here, plus X here. They're all 1-to-1 ratios, so that makes it easier. At equilibrium now, phosgene would be 0.01 molar minus X. And our products, carbon monoxide and chlorine, will be X's. Okay, so now again we set up our equilibrium expression in terms of our concentration of products divided by concentration of reactant. Right, and we can now plug our expressions in from our reaction table. And that equals 8.3 times 10 to the minus 4. All right, we can now kind of work through this to solve. So this would become x squared equals 8.3 times 10 to the minus 4 times 0.01 minus x. Okay. And we distribute, if we distribute this side through, what do we get? We get x squared equals, let's say 8.3 times 10 to the minus 4 times 0.01 minus 8.3 times 10 to the minus 4 times x. Now if we move x squared to, we'll keep x squared on that side, subtract the stuff from the other side on both sides, and what would we get? We'd get x squared plus 8.3 times 10 to the minus 4 x minus 8.3 times 10 to the minus 6, because that's what that would equal. And all of that would then be equal to 0. This should look kind of familiar to you. It's a quadratic. We have an x squared term, an x term, and then a term without a x in it. So to solve this, you can either sometimes there's ways to simplify it, the algebra. If not, you have to use the quadratic equation. And so this is an example of when we have to use the quadratic equation. And sorry, just kind of messed that up. This is a minus 4. Right, so the quadratic equation, just to remind ourselves, x equals minus b plus or minus the square root of b squared minus 4ac divided by 2a. Right? And a would be the coefficient out in front of the x squared. B is this coefficient, 8.3 times 10 to the minus 4. And c is 8.3 times 10 to the minus 6. So we can plug all of that stuff in. And when we do that, we get something like this. A is 1, which is easy. Okay. All divided by 2 times A, which again is just 1, so that's easy. All right, so then we're doing the math here, plugging it into the calculator. So x equals 8.3 times 10 to the minus 4. We have to do plus and minus. So let's do plus first. Plus that square root, all of that should equal 0.005821. Okay, and then divide that by 2. Well, what do we get for that? For that case, we would get x equals 0.0025 molar. And then we have to do the negative as well, so minus 0.83, 8.3 times 10 to the minus 4, plus, minus, doing the minus, 0.005821 divided by 2. And when we do that, we get a negative value. Right, so it's a negative value. Remember, you can't have negative concentrations. They don't make sense, so we can just ignore that one. Okay. We go back to our equilibrium table, our reaction table, our values at equilibrium. We can plug x in now for them, and therefore we have 0.01 molar minus 0.0025. So that concentration at equilibrium for phosgene is 0.0075 molar. And both of our products are just going to be X, which would be 0.0025 molar. Okay, so you can see it's actually much easier when you get to use the simplifying assumption in this case. But you can you're still able to solve for the concentrations even if you don't have that. Okay, the algebra just gets a little bit more complicated. Okay, our last question of the day. Research and development unit of a chemical company is studying the reaction of methane and hydrogen sulfide, H2S. They're two components of natural gas, and they react to form CS2 and 4H2 gas. Okay, in one experiment, we have 1 mole of methane and 1 mole of carbon disulfide, 2 moles of H2S, hydrogen sulfide, and 2 moles of H2 are mixed in a 250 milliliter vessel. At this temperature, the equilibrium constant is 0.036. Okay, so what you'll notice here right off the bat is you're starting with everything. You're starting with the compounds that are on the reactant side and the compounds that are on the product side. So our reaction table in the initial column, we're going to have to write values for everything to start. Okay, and that's going to make this much more complicated. Okay. So two parts to this question. A, in which direction will the reaction proceed to reach equilibrium? Right, so now what that means when you see that question, that means you're going to have to calculate a reaction quotient, Q, and compare that to an equilibrium constant. Okay, and then part B, if the methane concentration is 5.56 molar at equilibrium, what are the equilibrium concentrations of the other substances? So that's where we're going to actually have to use our reaction table. Okay, so reaction again is CH4 plus 2H2S goes to CS2 plus 4H2. Okay, so our equilibrium constant and reaction quotient, if we write those expressions, right, they're going to be products, which is CS2 times H2 to the fourth power divided by reactants, CH4 and H2S. Okay, so that'd be our expression for that. We're given equilibrium constant here as 0.036. And what we have to do is, before we can plug those concentrations in to determine our reaction quotient at the initial concentrations, we need to calculate those concentrations, right? So we're given a certain number of moles of all of these, and we're told it's in a 250 milliliter flask. Okay, so for methane, what concentration is that? We have 1 mole divided by 250 milliliters, which is just 0.25 liters. Okay, so that's 4 molar. H2S, that concentration would be 2 moles divided by the same volume, 0.25 liters. So that's 8 molar. CS2, sorry, that's 1 mole. Which again is 4 molar. And finally, H2. H2 is 2 moles divided by 0.25 liters, which is 8 molar. Okay, so those are all our concentrations. We can plug those in to our reaction quotient. So we get 4 times 8 to the fourth power and 4 times 8 to the second power. So you get a pretty large number on top and maybe not so large number on the bottom, and it equals 64. Having real trouble writing 4s today. Okay, 64. Now we can compare this to our equilibrium constant, and you can see that 64 is bigger than 0.036, so quotient is bigger than the equilibrium constant. And so what does that mean? That means your products, right, the things that are in the top there in your expression are more than they should be at equilibrium. And the stuff in the bottom, the reactants, are less than they should be. So that what that means is your product heavy in a sense, reactant light. So the reaction is going to go backwards, right, to the left in how this is written. Okay, so the reaction, therefore, reaction proceeds left. Right, so the second part of this is using our reaction tables to actually calculate a concentration. So methane plus 2H2S goes to CS2 plus 4H2. All right. So we have our initial concentrations, which we calculated on the previous, for the previous part. Right, and remember they are 4 molar and 8 molar, and 4 molar and 8 molar. So our change, right, our change is just going to be, we're going to, since this is going towards the left now, the compounds on the left are technically going to be our products. We're going to be gaining more of them at equilibrium compared to what we start with. So we're going to get a plus X for the change of methane and a plus 2X for H2S. And again, that 2 is because of that coefficient. And likewise, the compounds that are written on the right that we tend to think of as products, they're actually now reactants since the reaction's going backwards. And we're going to have a change of minus X and minus 4X for both of those. So at equilibrium, this would be 4 plus X. This would be 8 plus 2X. Here we have 4 minus X and 8 minus 4X. Okay. So now we need to solve for X. And how do we do that? Well, if we look back, we're given in this part an equilibrium concentration for methane at 5.56. So we know at equilibrium this is going to be 5.56 molar. Okay, so we can solve that expression, solve for X. So we know 4 plus X has to equal 5.56 molar. And when we solve for X, that's just going to be 1.56 molar. Right? So now we have the X value. We can just simply plug that in to our expressions for all these others. So H2S would become 8 plus 2 times 1.56, which would be 11.12 molar. CS2 will be 4 minus 1.56, which would be 2.44. And finally, H2 is going to be 8 minus 4 times 1.56. And that will be 1.76 molar. Okay. So those would be our concentrations at equilibrium. If we just write this more clear down here, Methane is 5.56. That's what we're given. We use that to solve for X, and then plug that into our expressions we have in the reaction table, and we get 11.12 molar for H2S, 2.44 molar for CS2, and 1.76 molar for H2. Okay, this slide just sort of summarizes the steps in solving an equilibrium problem. Okay, you need to first and foremost write the balanced chemical equation. You need to then write the expression for your reaction quotient, convert all amounts into the correct units, either molar if you're doing concentrations or atmospheres if you're using pressure. Okay, then you work on your reaction table. The reaction direction, if it's not known, you have to compare Q with K to determine which direction you're going. Okay, and then constructing the table. Okay, and remember, constructing the table, you do initial concentrations, which you're usually given, the change, which you're using the variable X, and then what it is at equilibrium, which would just be the initial value plus whatever the change is happening. Okay. Once you do that, then you can solve for X at the equilibrium quantities. Okay. Usually you're going to be given enough information to do this. So substituting those quantities that the expressions you get in your reaction table into that expression for Q, and then doing the algebra. And again, to simplify the math, you can assume that X is negligible in cases where you have a very large reactant concentration relative to a smaller equilibrium constant. Okay. And then finally, once you solve for X, then you can go back to those expressions in your reaction table, plug the value you get for X into them, and you can get the concentrations, solve for the concentrations of everything at equilibrium. Okay, so next time we'll finish chapter 17. The last section talks about Le Chatelier's principle, and this is how systems that are in equilibrium respond to changes. And then we'll also mention a little bit, go back to chapter 20, the last section of chapter 20, where we use K, equilibrium constant, to find delta G.